Set builder notation is a way of defining sets, and we do two things. We use these closed brackets or these curly braces to determine, hey, this is a set. Then what we have is we have this vertical line that separates our objects and the constraints on the objects. Our object is describing what our object is. Is it shapes? Is it marbles? Is it real numbers? Is it functions? Whatever those objects are, we define what they are before this vertical line, and it's our object. And then this vertical line, or sometimes a colon, is the term such that. And after that colon or vertical line, we constrain the objects. So the example we have here is if we have a collection of marbles and we would like a set containing only the blue marbles, we'd write it as follows. S equals the set of marbles such that the marbles are blue, which is another way of saying the set of blue marbles. With this notation, we're able to start looking at intervals and solving inequalities. So solving equalities, inequalities, and defining intervals is a real important part of mathematics. Especially in calculus, we use it a lot to define our domain and range, or where for what input values the function is defined, what output values does the function output to. Now, there are 5 equalities and inequalities that we use for real numbers, and this is for real numbers. And we have equals, means that A is equal to B, A strictly less than B, A less than or equal to B, A strictly greater than B, and A greater than or equal to B. Now, notice the difference between these two. In the first example here, A cannot equal B, but in the second line, A can equal B. Likewise here. Now, when we have constraints, there are certain things that we can do. So if we have an equality, A less than B or A greater than B or some equality, we can add an element to both sides or subtract an element to both sides, and we maintain our equality. Now, if we have an equality and C is a positive number, then our equality stays the same. But if we have an equality and we multiply by a negative number, our equality reverses direction. Now, with this, one of the obvious questions is, how do we solve equalities? Well, this is a simple example. We want to find all values of x such that we solve. And we're going to use these 3 properties. Right? The first thing I'm going to do is I'm going to add and subtract values to both sides such that I get x all on one side and numbers all on the other. So I'm going to get 3x minus 2x plus 1 is greater than 2x minus 2x minus 3. Which implies that this implies that x plus 1 is greater than minus 3. Well, I can now, x plus 1 minus 1 is greater than minus 3 minus 1. I can subtract 1 from both sides, giving me that x is greater than minus 4. And all values of x greater than minus 4 give us our equality. So how could I represent this using set builder notation? Well, it would be x in the real numbers such that x is greater than minus 4. But there's 2 ways we represent these intervals typically. This is set builder notation. But we also have something called interval notation. Set builder notation we've discussed before. We use brackets, curly braces to define our set, and then we have our object and our bounds on the object, or our constraints, which will be bounds on it. With interval notation, what we have is we have round brackets to represent not including the numbers, square brackets to represent including the numbers. The left-hand side is the lower side, so the right-hand side is the bigger side. To get used to these intervals, what we're going to do is we're going to take these notations, we're going to take the interval notation, we're going to draw the first couple using interval notation. Then we're going to look at the set builder notation, draw a couple more. And then in the last few, I encourage you to verify for yourself what we've drawn. So here we're going from A to B, which we'll mark A here. We'll mark B here. Okay? And we're not including A or B because we have round brackets. So we use an open circle to mean not A and not B. And that would be our interval. Okay? Here, we're going to include A because we have a square bracket and not include B. So if I have A, then B, I'm going to include A by drawing a circle and not include B by drawing an empty circle. Now, I can not have lower bounds or upper bounds. And you'll see this infinity, if we have an infinity with an open bracket, what that means is I'm going up to infinity, or I'm just going up. So here we're not including A, but we're going up and we never stop. So we draw that by drawing an arrow to the right direction. And here we do include A, and we go positive to infinity. Now, let's use our set builder notation to understand this interval. Here, our set builder, our constraints are not including A up to, but including B. So if I have A and B, I don't include A, I'm greater than A, and I go up to, and I do include B. Here it's saying X is between A and B, and we include both. So we include A, we include B, and everything in between. Here we're saying we're strictly less than B. So because I'm strictly less than B at B, I do not include B. I do not include B. It's everything less than. Oh, there's a funky figure. And now here I am less than or equal to B, so I'm going to include B. I'm everything less than. And that's our interval notation. So if we use our interval notation and our set builder notation to represent our previous interval, well, we have our set builder notation. But if I want to define the interval, well, it's everything greater than -4. So it's -4, not including -4, because it's a strict equality, up to infinity. But now that we've defined intervals, can we combine intervals? Can we take two intervals and combine them in some way? And we don't have adding intervals or subtracting intervals. What we can do is we can take the union and intersection of intervals. So to take the union of intervals, remember that the union of sets, the union of two sets is every element in either set. So all we need is we need to be in one set or in the other set. And to describe union, we use or. So it's in one set or the other set. So here, to take unions of intervals, I typically use the following three steps. We draw out our intervals on separate number lines, stacking them on top of each other. Then we draw a new number line, and the intervals that contain every number that is in any of the lines we just drew. Then we express the new intervals using a union of disjoint intervals for interval notation, or the word or in set builder. So let's take a look at an example where we compute the union of the following intervals. Well, I'm going to start with -2, and it's open up to 5. It's going to be open as well. And then I'm going to go from, so that's my first interval. My second interval is from 3. So let's say this is 3 up until 8. And here 3's not included, but 8 is included. And I have this interval. And now I go from -4 to -3, but I don't include -3. And now what I like to do is I like to just draw vertical lines down at all my points here. And I take everything that's in any of these spaces. So if I go from left to right. Oh, -4, I hit something. And I go up and I stop hitting things at -3. We're just going to increase the size of the thickness here. And now nothing, nothing, nothing until -2. And then I keep hitting things all the way until 8, and I include 8. So I'm going from -2 until 8, and I keep hitting things. And now I want to express this set here. Well, this set here is x in, I include -4 up until -3, union with, not including -2, up until and including 8. But this interval notation is really nice here. But what about set builder notation? Well, I'm taking x in the real numbers such that -4 is less than or equal to x, which is less than -3, or -2 is less than x, which is less than or equal to 8. And we use the word or to represent x is in this interval or x is in this interval. If we use the word and, it would be required to be in both intervals. Now let's take a look at intersection. Now, intersection, remember, intersection of two sets is the elements in every set. So I'm going to use a similar process here, but now instead of taking any, I'm going to take all lines. So I'm going to take the values that intersect all lines. First, we're going to draw out each separate constraint, stacking them. Then we're going to draw a new line, and we're going to look at the intervals on the line that intersect with all three or all of the lines we've drawn above. We're going to express this new interval using a union notation for disjoint set intervals in our new line and the word or in our set builder notation. Now, when we're looking at expressing a set, the easiest way to understand it is typically with disjoint unions. So if we look above, this interval is easiest to understand, not with these unions where I have intersections, but when I have the disjoint union of sets. So I want to figure out the easiest way to express that, and same here. Now, at the end, I want nice disjoint unions. But let's start with, we have -2, I'm not including, up until 5 that I am including. And now I have 3 that I'm not including, up until 8, which I am including. And finally, I have from -4 that I am including, up until 4, which I'm not including. Once again, I'm going to create these vertical lines to highlight the points where things change. Now, when I look vertically, I would like to see where all 3 lines are overlapped. So if we look here, none of the lines are touched, so not all 3. Well, here I have 1, but I don't have all 3. I have 2. I still do not have all 3. Well, here I touch all 3 lines, but that doesn't happen at -3, or at 3, sorry. But beyond 3, it does. And at 4, it no longer touches all. So I don't include 3 and I don't include 4. Everything in between is included. Well, what's my interval notation? Well, x is in 3 to 4, not including 3 and not including 4. Whereas my set builder notation is x is a real number such that 3 is less than x, which is less than